So at this point, here are the things you're going to need. First of all, regardless of how far you got in class, you're going to need your calculator and your periodic table at this point. Depending on how far you got, everybody should have at least started empirical formulas. If you got farther than that, I just want you to fast forward your way through until you basically get to the part that we didn't cover yet in class. So make sure you don't have to listen to stuff that you've already heard. So starting from the very top, an empirical formula. Empirical formulas, what are they? I say it has nothing to do with the Roman Empire or the Empire in Star Wars. Unfortunately, that would be awesome. But an empirical formula represents the lowest ratio of atoms in a compound. The lowest ratio of atoms in a compound. For example, something like hydrogen peroxide, H2O2, that's not the lowest ratio. The empirical formula of hydrogen peroxide would just be HO. It's the lowest ratio since they're both divisible by a common factor of 2. So that's what the empirical formula is. Now let's look at this question down here. The molecular formula, how does the empirical formula differ from the molecular formula? Molecular formulas are the actual formulas for the compound. The actual formula for the compound. And so as an example, we give you two sugars here, glucose and ribose. Now if you'll notice, these two have different formulas, C6H12 versus C5H10O5. But you'll notice they have the same empirical formula. Do you see how both of these are in a ratio of CH2O? You can divide 6, 12, and 6 by a factor of 6, 5, 10, and 5 by a factor of 5. So while these components have different molecular formulas, these both have the same empirical formula. And usually when we're talking about empirical formulas, we'll abbreviate it EF. So just keep that in mind. When you see that, I'll use that equation very often to abbreviate. So again, that's the idea, is empirical formulas, lowest ratio, molecular formulas are the actual formula for the compound. Okay, so at this point you have shown how you understand how to do percent composition. This is one of my favorite nerdy math things that we do in this class. How do you calculate an empirical formula? Very often you'll see us do this. You'll be given percent composition data and asked to find the empirical formula. And there's a fabulous little rhyme that we have here, the Ode to the Empirical Formula, that teaches you how to do that. And the ode looks like this: percent to mass, accidentally spelled with 3 S's, just ignore those. Mass to mole, divide by smallest, and multiply till whole. And what this will do is, this is, like I said, a fun little rhyme to help you convert from percent composition values into an actual empirical formula. So here's how we go. Let's look at our example. Methyl acetate is a solvent used in paints, inks, and adhesives. Really, what we want to hone in on is this information right here. It gives us 3 elements that make up methyl acetate and their percent compositions. So what we need to do is, there are 4 steps here, and that's, this little rhyme is going to help us go from percents into an empirical formula. This little note right here is important. It says, assume that you have 100 grams of the compound. If that's the case, the percentages will be equal to the mass of each element in grams. Okay, what the heck does that mean? That means that, assume that we have 100 grams of this. If that's the case, we're going to have 48.64 grams of carbon. 8.16 grams of hydrogen. So step 1, percent to mass, it's really easy. All you do is you take the percent amount and just stick a gram unit on it. You take out the percent and replace it with a gram. So we're going to organize these by elements. So here is our carbon. Scooch this down here. Our hydrogen and our oxygen. Okay, so we have 3 gram measurements. Our second step is we're going to be converting mass into mole. So this is where you need your calculators. If these are going to be T-charts, and you need the molar mass of each element. So here we go, setting up our T-chart. I know that the molar mass of carbon is 12.01 grams into 1 mole. and we're going to get a value. I set these all up at once. Hydrogen, 1.008 grams, 1 mole. And then the same thing with oxygen, 16.00 grams into 1 mole. And then the next step is to just do the math for all of those calculations. So 48.64 divided by 12.01 gives us, and now this is where things get a little interesting. All this work that we've had you do with sig figs, actually you kind of get to ignore for the moment, just for the moment. But we get a number like that. And then for our next one, 8.16 divided by 1.008, and we get 8.095. It's keeping 4 sig figs. Technically, I should only have 3, but you'll see in a moment why that actually doesn't really matter. And we have 43.2 divided by 16. And so then when we divide those two, we get 2.7. Okay, so that's taken us through step 2. We've done mass to mole. Step 3, divide by smallest. So we've gotten 3 numbers here. What we're going to do is divide every number that we've gotten by the smallest number, in this case 2.7. So again, we're just going to do kind of these in a big series. 4.049 divided by 2.7 gives us approximate, and this is why sig figs start to not matter. We get 1.49962. I'm really going to round that to the nearest half. I'm going to say, okay, that's really, really close to 1.5. And you'll see in a moment why I can do that. And then for this next one too, in my calculator, I get 2.998. Really, I'm just going to round that to 3. And then my last one, 2.7 divided by 2.7, that's going to be equal to 1. So now what I have is I have 3 numbers. And step 4 is going to help me convert these numbers all into whole numbers. If you look, I have 1.5, 3, and 1. Well, 3 and 1 are already whole numbers, but 1.5 isn't. What I can do to make that a whole number is simply double it. But when I double 1.5, I have to double every other number that I'm working with. So when I multiply each of these by 2, I'm left with 3, 6, and 2. These numbers that I've just found here tell me how many of each type of element is in my compound. So the 3 corresponds to the carbon, so that formula is C3. 6 here makes H6. 2 here makes O2. So this is the empirical formula for methyl acetate using that ode to the empirical formula, percent to mass, mass to mole, divide by smallest, multiply till whole. Okay, we're going to try one more together. Okay, so let's take a look here. In this one, again, same kind of thing. We're given a certain compound yielded the following percentages of elements by mass. So we're told we have nitrogen, hydrogen, carbon, and oxygen. So this one is good only because we have a lot more elements to work with. Okay, so I'm going to designate one line for each of the 4 elements involved. Okay, so here we go. Nitrogen, remember step 1 is percent to mass. All that means is I just take the number and take off the percent and stick a G on the end. 8.392 grams, 12.50 grams, and then oxygen 49.94 grams. Okay, so that's step 1, percent to mass. Step 2, mass to mole. I want you to set up 4 T-charts, and even if you'd like to challenge yourself, you can pause the podcast and then try it and then hit play again and see if you got it. But again, so we have the molar mass. The nice thing about these is you will get very good at memorizing molar masses on the table because you'll use the same ones over and over again. Okay, so here we are. Let's start plugging these through. So 29.16 divided by 14.01 gives me 2.08. And again, we'll keep track of sig figs, but remember that when we do that divide by smallest step, sig figs kind of get ignored only for that one time. Here we have 8.325, 12.50 divided by 12.01 gives us 1.041. And then lastly, 49.95 divided by 16 gives us 3.12. So again, let's bring it back to our little rhyme, our ode. So we have percent to mass, which we've done here, mass to mole, which we did here. The next step is divide by smallest. So okay, so I have these three numbers. This one is the smallest, so I'm going to divide every number here by 1.041 all the way across the board. And I'm going to get four different numbers. And remember, this is the part where, wonderfully, you get to kind of ignore significant figures. So again, when I do this first one here, I get a number that's 1.999. Really, I'm just going to call that a 2. Our next one, 8.325 divided by 1.041. And I get 7.997. Really, what am I going to round that to? That's really an 8. I know that's going to be a 1. And then for our last one, 3.12 divided by 1.041. For that one, I get 2.997. Really, I'm just going to treat that as a 3. So we have our final step, which is multiply till whole. Now in this case, we're already there. Every single number that we have is a whole number, so we don't really have to do anything for that last step. So again, what that tells us is all of these numbers tell us the quantity that each element will appear in the compound. So our final answer, the empirical formula, is N2H8CO3. So this is the empirical formula of the compound. All right, so for the rest of your homework, the expectation is that you're going to try this one on your own and then come to class with that one all complete. We're going to do the rest of the handout, the one that starts with molecular formulas. We will do that as a class tomorrow. But again, so your only homework is going to be to finish this one up and come with an answer for an empirical formula for the magnesium salt. Okay.